Hello everyone. Now I am going to present our paper KGSecConfig, a knowledge graph based approach for security container orchestrator configuration. Authors are myself, Mubin Haque, Mehdi Kholoosi, and Babar. We are from the CREST research group, University of Adelaide, Australia. And this research is partially funded by Cybersecurity Cooperative Research Centre, Australia. Here's the outline of our presentation. First, a brief overview of our research, followed by motivation, methodology, results, and some implications. I will also discuss some of the limitations, and finally, the presentation will be concluded with few research directions. First of all, I am going to briefly describe about our work. Container Orchestrator, or CO, is a vital technology for managing clusters of containers, which may form a virtualized infrastructure for developing and operating software systems. Like any other software system, securing the container is critical, but can be quite challenging task due to large number of configurable options. Manual configuration can be not only knowledge intensive and time consuming, but also is error prone. For automating security configuration of CO, we propose a novel knowledge graph based security configuration KGSecConfig approach. Our solution leverages keyword and learning models to systematically capture, link, and correlate heterogeneous and multi-vendor configuration space in unified structure for supporting the automation of security configuration of CO. We implement KGSecConfig on Kubernetes, Docker, Azure, and VMware to build security configuration knowledge graph. We demonstrated that our knowledge graph based approach can help in addressing several challenges such as misconfiguration of security associated with manually configuring the security of CO. Although automation is highly desirable for securing the configuration of CO to reduce the required effort and minimize the risk of misconfiguration, automation support may need to overcome several challenges such as configuration data scatteredness, dynamicity, and overload. Firstly, data scatteredness. Orchestrators is typically integrated with multi-vendor software systems such as continuous integration and development or deployment CI/CD tools such as Jenkins, development and operations platforms such as Docker, and cloud resource providers such as Azure. Therefore, administrators need to investigate each of the scattered tools, platforms, or providers' configuration space for identifying and capturing the secret configuration values and options. Secondly, cybersecurity data overload, as the number and the sources of threat advisories are increasing. While threat advisories contain in-depth information on how attackers target the existing configuration to compromise the software systems, it is cognitively challenging task to separate the relevant from the irrelevant information. For example, to obtain the secret configuration options for Kube API server, one of the 8 constituent components of Kubernetes, relevant documents contain 400 sentences on average, whereas the concepts, that is, relevant sentences, reason, implementation details are 30 sentences on average. Thirdly, CO security configuration options data may dynamically change due to new vulnerabilities, malware, security flaws, and patch releases. For example, the configuration option for the argument image pool policy in Kubernetes was expected to change after a DDoS attack on Datadog. Hence, to mitigate the rapidly changing threat landscape, configuration space needs to be updated continuously, which requires a frequent manual monitor and search the diverse data sources such as HTML, JSON, or XML. There is a need for a unified solution for secure CO configuration, consulting configuration space associated with secret arguments, options, and concepts of heterogeneous and multi-vendor software systems for enabling automation of secure CO configuration. To address the above identified problem, we propose to build a knowledge graph by continuous monitoring and correlating the required knowledge for security configuration. This can provide a fundamental support for automatic security configuration of CO. This is the approach that we followed for KGSecConfig construction. There are 3 modules: configuration knowledge graph construction, security document relevancy estimation, and lastly, security configuration concept classifier. In first module, various software systems that can be used in orchestration are considered and extract their configuration space from documentation. We formulated a configuration knowledge graph using a predefined configuration schema and this configuration space. This will also support in module 2. In module 2, various security documents such as threat advisories or white papers are considered as source of secret configuration option and values. Using those options and values as keywords, we identify documents related to security configuration. In module 3, we used a learning model to determine several key concepts such as reason, statement, and implementation details required for configuration. After extracting security concepts, we added such concepts to the initially built configuration knowledge graph for security configuration knowledge graph construction. In next few slides, we provide some examples to better visualize our approach. In the left side of the figure, we can see an example of configuration space with argument, type, default options, descriptions, and available options. With this information, keeping arguments as the root node, we built an initial configuration knowledge graph which is shown at the right side of the slide. Here, we can see an example of configuration document and a non-configuration document. We used configuration argument such as authorization mode and its associated presence of options such as RBAC to configuration document relevancy estimation. Then the sentences in the configuration documents are passed to a learning model to identify the key concepts. Then those key concepts are added to the configuration knowledge graph to build a security knowledge graph. Those green nodes are added to the previous knowledge graph to build the final KGSecConfig. Our evaluation results showed that we achieved good performance in terms of keyword-based method for estimating the relevancy of configuration document. For machine learning-based approach to localize and extract the key configuration concepts, combination of word and character level features perform better than other features. Lastly, we observed that logistic regression model takes the least amount of time than other models. Since the latest industrial practice is highly focused on cost-effective solution that means optimum performance with minimum resources, we suggest to use logistic regression-based method for KGSecConfig construction. Here, we showed some of the implication of our proposed KGSecConfig. Firstly, it can be used as an automated service for security configuration. That means for a given configurations file, such as deployment configuration for a virtualized software system, our KGSecConfig can detect and fix prevailing misconfiguration in the deployment configuration. This figure shows the overall pipeline for that purpose. In next few slides, we'll demonstrate that in details. Here we can see a deployment configuration, and from that configuration, we built a parse tree with kind argument as the root node, and leaf nodes are constituted of options or values associated with that argument. Formulation of parse tree, right side of our slide, is the preprocessing step. Then from the configuration parse tree, we automatically check and then detect the misconfiguration occurrence of the given configuration. Here the red circles are identified as misconfiguration and green circles represent that the modification addition that is required for the secured option or value to that misconfigured argument. Our KGSecConfig with argument and secured option values helps in preservation of the relationships and able to generate the required options in appropriate syntax. Finally, from the output of the compliance checker, we generate the deployment configuration in YML format. Our second implication is that our KGSecConfig can provide the reasoning why we need to set or enable or disable a particular set of arguments that can increase the understanding of the configuration knowledge. For example, false option in profiling argument reduces the potential attack surface since the default true option generates a significant amount of program data that could potentially be exploited to uncover system and program details. Our KGSecConfig systematically organizes such essential knowledge by has-goal relationship with respective options which can help administrators reasoning in configuring CO. In third use cases, we showed that our KGSecConfig minimizes the manual traversal of multiple data sources required for an investigation to change the configuration options due to the disclosure of a new security issues such as vulnerabilities or malware. For example, a denial of service vulnerability of Kube API server is revealed in one of security information sharing sources, which is vulnerability database NVD. This vulnerability can be fixed by restricting unauthorized access to Kube API server, which had been mentioned in another source, that is security announcement of Kubernetes. However, neither NVD or that announcement site described how to restrict unauthorized access to Kube API server in terms of configuration options and arguments. Our KGSecConfig can correlate such encapsulated knowledge with the goal concepts associated with the arguments of Kube API server and the query restrict unauthorized access to Kube API server, and then can return the mitigation approach by providing necessary arguments and options, which is anonymous auth will be false and authorization mode will be RBAC to restrict the unauthorized access. Therefore, KGSecConfig can automatically provide the knowledge required for security configuration to fix emerging cyber threats. Our KGSecConfig can support to visualize the configuration hotspot, that is the arguments which need to change the default options for security purposes. The default configuration in CO and its integrated software are not always security focused and require changes to harden the CO. Multiple cybersecurity attacks were launched due to default configuration in Kubernetes. For instance, Tesla went through a cyber breach because of misconfiguration in 2018. Unauthorized users got access to secret resources exploiting an administrative CO which was being operated with default configuration in Tesla. Besides, the diversity of tools, platforms, and resource providers' configuration space makes it quite challenging to locate and then update such configuration manually. For example, the lead engineer of Target, a retail corporation, reviewed Kubernetes as no document versioning, stuff is all over, and it is quite difficult to find the right stuff. In this regard, our KGSecConfig can be a potential approach to mitigate this challenge by visualizing a unified knowledge base. Here, we present a subgraph which has been built using Neo4j, providing the configuration hotspot of the studied software systems. This figure or this approach can be a way to represent which software system needs to adjust its default arguments more than the other software systems and can help practitioners to prioritize their security configuration task. Here we present our threats to validity and some limitations. Label data are necessary for training a supervised learning model. Our manually labeled dataset may be biased and subjective. We followed the prior studies to mitigate the bias. Two authors independently annotated the dataset and reported the disagreement. Secondly, our collected configuration options from official documentation might be incomplete. However, prior studies on configuration mining from question and answering sites and bug reports also leveraged official documentation in their studies. Besides, our security configuration arguments are derived from publicly available security information sharing sources, which might miss some security configuration arguments. However, we used security information sharing sources reported by prior researchers in the security of orchestrators or software systems. In future work, we will investigate other sources of security information. Thirdly, our evaluation results consider 4 case study software systems and 5 machine learning models. We cannot generalize our findings to other software systems or machine learning models. However, we provided an approach that can be applied to any other software system. Besides, our selected software systems has a large configuration space and is popular in orchestration services. Moreover, our goal is not to compare among different machine learning models, and any learning-based model can be plugged in to our approach to build the knowledge graph. 85% of global organizations are forecast to relocate their on-premise application to container-based development and deployment. Container orchestrators such as Kubernetes are playing a vital role in managing container clusters in both the development and production environment. Container orchestrators require automated configuration for secure operation of container clusters. The diversity of software systems used in orchestrators, their vast configuration space, and information overload cause barriers for automating the secure configuration. We proposed a novel knowledge graph-based approach, KGSecConfig, to aggregate and organize disparate silos of security configuration knowledge. We plan to extend our KGSecConfig to explore the potential of security configuration migration from one orchestrator to another orchestrator for the clusters. And another potential approach will be to identify and extract the configuration dependency among diverse software systems to realize their secure operation. We want to thank Cybersecurity Research Center and also the supercomputing resources provided by the Phoenix HPC service at the University of Adelaide. Thank you everyone for your patience sharing. I would be really happy to take your questions and comments. You can also visit in our preprint of the paper in the mentioned link. Thanks again.